Hello and welcome. My name is Niall McGuire. I'm a first year PhD student at the University of Strathclyde, and today I'll be presenting my 2023 ACAIN paper submission, What Song Am I Thinking Of?, co-authored by my supervisor, Yash Armour-Shvege. Information retrieval aims to satisfy a searcher's information need. Many IR systems rely on the searcher to assess the information need and convert it to a format appropriate for the information retrieval system. However, during this conversion process, from the IN to the appropriate format, a semantic gap may appear between the searcher's authentic IN and the formulated query. As well as this, it's been found that even when a searcher is capable of representing their information need in a suitable query, they are often noisy and uncertain, limiting how accurately they can represent a searcher's authentic IN. Prior studies have attempted to alleviate this problem through the use of biological features extracted from brain activity to capture a better representation of the searcher's information need. Techniques used to extract these features often include fMRI, MEG, FNRIS, and EEG. Among these techniques, EEG has become prominent due to its high temporal resolution on the millisecond scale, its portability relative to the other techniques, and its unobtrusiveness. The field of neurosearch aims to incorporate these features into information retrieval systems in order to help bridge the gap between the subject's information needs and the query representation. The ability to understand and process information needs using these features offers a promising solution to address the issue of noisy and ill-defined queries. A subsection of information retrieval that may benefit from the use of biological features in its search process is music information retrieval. Instead of a subject having to rely on song titles, artists, and lyrics, a subject would simply be able to listen to or imagine a song and have the system retrieve it. Prior works have demonstrated the ability to classify perceived songs with accuracies varying from 24 to 52.5%. These results are encouraging but far from perfect. And more importantly, no prior works have been able to classify imagined songs solely from EEG data. As such, within this study, we propose 4 key research questions. Firstly, is it possible to classify a song from subjects' EEG data whilst perceiving a given song? Secondly, is it possible to classify a song from a subject's EEG data whilst imagining a given song? Next, how similar are perceived and imagined EEG data? And can they be used interchangeably for training and testing machine learning models? And lastly, how much of a song would a subject have to perceive/imagine before the system can produce accurate results? For this study, we utilised the OpenMIIR dataset for our source of the EEG data. The dataset itself contains the EEG signals of 10 subjects recorded using 64 plus 2 EEG electrodes, sampled at 512 Hz. The dataset was produced by having each subject perceive and imagine 12 short pieces of music 5 times, each to create repetitions. Each song ranged between 7 to 16 seconds in length, and each of the music segments were taken from various musical pieces across different genres. These songs were sometimes recorded with lyrics, songs where lyrics had been purposely removed, and some purely instrumental pieces. During EEG recording, it's commonplace for electrical activities caused by the individual's actions or the environment to cause artifacts or noise to form within the EEG data. These unwanted signal fragments can negatively impact the measurements and skew our results. As such, we need to remove these artifacts to ensure that we get the optimal results. Firstly, bad channels previously marked by the dataset creator were removed from the raw dataset. Then we applied bandpass filtering with frequencies ranging from 0.5 to 40 Hz, as literature has supported that most human brain activity sits within these specific ranges. As such, anything outside of these ranges can be considered external noise. Subsequently, we then applied independent component analysis, ICA, to identify and remove potential artifacts caused by the subject's blinking. To capture significant characteristics of the EEG data, we generated a set of features. Firstly, morphological features. This includes the number of peaks, the average nonlinear energy, and the curve length. Each of these were extracted at 4 specific frequency bands: theta, which is 4 to 8 Hz, alpha, which is 8 to 13 Hz, and beta, 13 to 25 Hz, and low gamma, 25 to 40 Hz. We then extracted statistical features, this being skewness, mean, and kurtosis, and then nonlinear features, these being the approximate entropy and the Hertz exponent of the EEG signals. In prior works relating to song classification from EEG data, machine and deep learning models have been used to effectively classify EEG data. As such, we make use of the following models in our work: Gaussian naive Bayes, support vector machine, gated recurrent unit, bidirectional gated recurrent unit, long short-term memory, and bidirectional long short-term memory. The architectures of each of these models can be seen in the table on the right, where each of the models is indicated with their unit count and their specific layers. You'll notice that the last layer is a dense layer with 12 potential outputs. This corresponds to each of the music stimuli that we're attempting to classify. To address each research question, we created several experiment scenarios. On screen you can see experiment scenario 1. This is the perceived and imagined song classification. This was designed to investigate research question 1 and research question 2. Firstly, our model performed song classification using the EEG signals of all subjects, except one subject. This subject was left out of the training set and used for testing purposes. The task was performed twice using 2 distinct groups of data. Firstly, the perceived dataset and the imagined dataset. Classification was performed for each repetition in the stage to determine the difference in model performance. On screen, we have the results from scenario 1. The left table shows the model's accuracies for the perceived dataset, and the table on the right shows the model accuracies when trained on the imagined dataset. As we can see for the perceived EEG song dataset, the LSTM is the highest performing model, with an average accuracy of 61.4%. This helps to address research question 1, demonstrating the ability of the techniques we employ within this study to provide higher classification accuracy than achieved by prior studies. When looking at the table on the right, we can see that the highest performing model is once again the LSTM, with a score of 60.8% accuracy. This helps to further address research question 2 by initially showing that the techniques employed within this study can classify songs solely from imagined music EEG data. As well as this imagined classification was within 2% accuracy of the perceived classification, demonstrating the comparable performance of imagined EEG data with perceived EEG data. On screen you can see the breakdown of experiment scenario 2. This was the train test data limitation, designed to investigate research question 4. We trained the models the same way as in scenario 1, however after completing the model training procedure, we tested our model utilizing n% of the initial dataset for each song repetition. The sizes of the testing dataset vary between 10%, 25%, 50%, 75%, and 100% of the complete dataset. On screen you can see the results for experiment scenario 2. For this plot, we're only using the imagined test set breakdown, as the results achieved by the perceived test set breakdown were almost identical. For this plot, the y-axis indicates the accuracy achieved by each of the models, whereas the x-axis indicates the n% of the test segment that was used to evaluate the models. Within this plot, we also have multiple subplots representing each model, as well as box plots that represent the variance of the scores achieved for each of the models. And the red triangle that you can see in the middle of the box plots represents the mean achieved by each model. When looking at the initial test segment size, which is 10% of the total test segment, we can see that the highest performing models are the GNB and SVM models, each achieving 30.5% accuracy. However, as the test segment continues to increase, these models' accuracy proceeds to stagnate, not changing significantly. However, When looking at further results, for example, test segment 50% and 75%, the highest achieving model is the LSTM. On 50% of the test segment, the LSTM model achieves 52.5% accuracy, and on 75% of the test segment, the model achieves 53.4% accuracy. A key consideration when looking at these results is that the average song length within our dataset is 7 seconds. This means that achieving 52.4% accuracy in classification across 12 song segments, the LSTM model is only using 3.5 seconds of a song. This helps to address research question 4, as we can see that our model produces somewhat reasonable classification accuracy using a very minimal segment of a song. On screen we have experiment scenario 3. This is where we interchange the perceived and imagined EEG music datasets for both testing and evaluation. This helps to address research question 3, as we're able to determine whether imagined and perceived songs can be classified interchangeably. Our models were firstly trained with the EEG signals from the perception stage and tested on the EEG signals from the imagination stage, and vice versa. Like the first experiment condition, we again rotated the subjects whose data was used to evaluate the model for both the perceived and imagined states. On screen are the results from this test scenario. For the initial case of training the models on the perceived dataset and evaluating them on the imagined dataset, we can observe that the highest performing model for this case is the BLSTM, with a score of 63.6% accuracy. Furthermore, in the case where we trained on the imagined data and evaluated on the perceived dataset, the model with the highest accuracy was the LSTM, with 61.4% accuracy. The results highlight the comparable nature of the perceived and imagined EEG song data. These findings help to directly address research question 3. To conclude, this study covered and explored the use of EEG data for participants whilst perceiving song segments and imagining song segments. We also explored the interchangeability of perceived and imagined data for model training and testing, and also investigated how test quantities of perceived and imagined data affect model classification. Our findings demonstrated classification accuracy of perceived songs higher than in prior works. Our findings also showed the initial ability to classify imagined songs with similar accuracy found in our perceived models. We also found that perceived and imagined data appears to be interchangeable for training and testing. And lastly, we demonstrated the ability to classify 12 song segments with around 50% accuracy using only 3.5 seconds of data for both perceived and imagined. And that concludes our presentation. Thanks for watching.